Welcome back. I am so thrilled you're joining me for today's explainer because we are looking at a truly monumental shift in how science is actually done. For centuries, our image of a chemist has been pretty standard. A human in a white lab coat, meticulously holding a beaker, testing just one reaction at a time. But today, well, we are moving way beyond that. We're stepping into this mind-blowing autonomous future where artificial intelligence isn't just crunching numbers in the background anymore. It's actively driving the discovery process.
So that brings us to a massive, slightly intimidating question we really have to ask ourselves. Is the era of human-only science over? See, modern science has kind of hit a complexity crisis. Researchers today are forced to analyze massive data sets, incredibly complex molecular systems, and these vast tangled reaction networks. Honestly, it is simply too much multidisciplinary information for the human brain to handle alone. We literally need help.
Okay, let's dive right into this. Here is our roadmap to make sense of this massive shift. We'll start with the AI chemistry revolution, step inside the autonomous lab, and look at designing the future molecule. Then, we'll explore chemistry for a greener world, tackle the ethics of AI science, and finally, wrap things up with the human-machine partnership. All right, Section 1, the AI chemistry revolution. To really understand where we're going and why it's such a game changer, we first need to look at how chemical discovery has historically evolved. Basically, chemistry has progressed through a few distinct eras. It started with Era 1, which was purely experimental, trial and error right there in the physical lab. Then came Era 2, theoretical chemistry, where we started using mathematical models to explain behavior. Era 3 gave us computational chemistry, utilizing computers to accelerate our simulations. More recently, we've been hanging out in Era 4, AI-powered chemistry, where machine learning acts as an assistant to help us find things. But Era 5 at the very end there, that is the catalyst pushing us completely forward. Autonomous scientific discovery. We're crossing the line from AI being a helpful little assistant to systems that independently conduct actual, legitimate research. Moving on to Section 2, inside the autonomous lab. Now, what does Era 5 actually look like in the real world? Well, what's really interesting here is that it starts with this concept called a digital twin. Basically, before physical chemicals ever even mix, we build a perfect virtual representation of a physical system, whether that's a single tiny chemical reactor or an entire massive manufacturing plant. By running simulations on this digital twin, scientists can run predictive analysis, optimize the entire production process, and drastically reduce risks, all while monitoring everything in real time. It's kind of like a flight simulator, but for chemistry. But the real magic happens when that digital world crashes into the physical one in an autonomous, self-driving laboratory. Let's walk through a typical day in the life of an autonomous lab. First, the AI designs the experiments. Then, physical robots actually conduct those experiments, pouring, mixing, the whole shebang. Next, automated instruments collect the resulting data, which the AI immediately analyzes. And based on whatever it just learned, the AI proposes brand new experiments. This cycle just repeats, continuously, 24 hours a day, 7 days a week. It accelerates discovery, pretty much slashes human error entirely, and massively increases our productivity. Which brings us to Section 3, designing the future molecule. So now that we have these incredible sci-fi level autonomous labs, what exactly are they making? Well, the AI isn't just crunching old numbers anymore. It's using generative AI, technologies like transformer models and diffusion models, to create entirely new chemical structures right from scratch. We are talking about novel pharmaceuticals for drug discovery, brand new catalysts to speed up reactions, advanced polymers, and cutting-edge nanomaterials. By just defining a desired property, the AI goes ahead and generates candidate molecules, evaluates them, and picks the absolute best ones. It's actively expanding our known chemical space, and it's doing it way faster and at a much lower cost than we ever could before.
Next up, Section 4, Chemistry for a Greener World.
And this brilliantly illustrates how AI chemistry isn't just confined to some abstract laboratory beaker. It's actually addressing humanity's most pressing issues across the board. We're seeing roughly a 20% impact right across these major sectors. Healthcare, with much faster medicine development, clean energy through designing better batteries and solar tech, and broad sustainability efforts to lower our environmental footprint. It's even pushing the needle 20% in food security by improving agricultural chemistry, and another 20% in water purification through advanced treatment tech. An absolutely huge part of this global impact falls under green chemistry. The primary objectives here are clear, and they are so important. We need to reduce waste, minimize energy consumption, eliminate toxic substances altogether, and lower environmental pollution.
AI is actively tackling these exact goals by using machine learning to identify highly sustainable reaction pathways and environmentally friendly solvents. In the real world, this means cleaner production facilities, reduced emissions, and a really powerful push toward a circular economy where we minimize waste by reusing and recovering materials. All right, let's pivot to Section 5, the ethics of AI science.
Okay, with systems this powerful, we really have to acknowledge the elephant in the room: safety and transparency. A major challenge in AI science is what we call the black box problem. That's when an AI spits out an answer, but we have absolutely no idea how it got there. That is exactly why explainable AI, or XAI, is so incredibly critical. XAI is literally designed to help human users understand the model's decisions, see which features were most important, and grasp the actual rationale behind its predictions. Because think about it. Chemists simply cannot blindly follow an AI's recommendations. They need this transparency to build trust, improve adoption of the tech, and safely advance our scientific understanding.
So the crucial point is that when we evaluate these systems, we have to establish a really cohesive ethical framework. That means asking the tough questions. How are these predictions actually generated? Who exactly is accountable when an autonomous lab makes a critical decision? We also have to make sure that these AI models are fair and unbiased, while carefully considering if these powerful new chemical discoveries could potentially be misused by bad actors. To mitigate these risks, it is just absolutely essential that researchers strictly validate all results experimentally, follow rigorous safety protocols, and above all else, maintain constant human oversight. And finally, Section 6, the human-machine partnership. Which brings us to the question probably lingering in the minds of a lot of scientists today. Are humans going to be entirely replaced by machines in the lab? Well, the reality is defined by a really stark contrast in our respective strengths. Humans bring creativity, intuition, deep scientific reasoning, and that crucial ethical judgment we just talked about, qualities a machine simply does not possess. On the flip side, the AI brings unparalleled data analysis, rapid-fire pattern recognition, tireless automation, and process optimization. So the future won't involve AI replacing chemists entirely. Actually, human creativity combined with AI data analysis produces significantly better outcomes than either one could ever achieve working alone. Because of this amazing partnership, the future isn't about job loss. It is entirely about job evolution. We are seeing these really incredible emerging careers pop up all over the industry. We're talking computational chemists, pharmaceutical AI researchers, materials informatics specialists, and autonomous laboratory engineers. To really thrive in these new roles, the next generation will absolutely still need their fundamental chemistry knowledge, for sure. But they're going to need to combine it with programming, statistics, data science, and machine learning skills. Let's move to our final takeaway and see how this all builds together. The source material puts it perfectly, saying the future of chemistry will likely be defined by a partnership between human intelligence and artificial intelligence, working together to solve some of humanity's most important challenges. It really is not human versus machine. Not at all. It's human and machine, teaming up against the immense challenges of our time. Which leaves us with this final, lingering question for you to ponder. How will you use AI as a partner to empower your own creativity and solve tomorrow's massive challenges? Whether you're a student, a seasoned professional, or just a deeply curious learner, the tools to build the future are literally right here. Thank you so much for joining me on this explainer. Keep learning, stay curious, and I'll catch you next time.